All right, so here's another example reaction. So what we're going to do is go from an ester to a carboxylic acid. When we make the carboxylic acid, there's a little bit of a wrinkle in the mechanism because it's an acid and it can kind of do a further reaction. So if we start with an ester, right, just any old ester, and react with a strong base, let's use sodium hydroxide, which will simplify just to hydroxide. And it's going to follow that first usual step. Right, so nucleophile adds, comes down, bumps off a leaving group, messed up my OH there a little bit. But there's two things going on with this reaction. So in terms of leaving group, OCH3 is not very good, right? Comparing that leaving group ability to hydroxide, OH minus, if we compare these two things, well, actually this one is worse, right? This reaction shouldn't really be favored that well in the forward direction because the methyl group here can donate some electrons to the oxygen, making that even more negative. All right, so why does this reaction work? And in fact, it's in an equilibrium. So we'll use double arrows. This can kind of go back and forward, right? So why not have this come in and replace, get us to the middle point? You know, it basically can go in the reverse direction. And the reason why this reaction does actually work, though, is because we've made an acid here, right? So carboxylic acid, forgive my poor drawing, is a weak acid. So as soon as this is formed, it'll do another step, right? We'll actually go on here then. Is another proton transfer reaction. Making the much more stable methanol leaving group, and then also the much more stable deprotonated carboxylic acid, right? So if we're comparing reactivity, hydroxide's pretty reactive, you know, good nucleophile, bad leaving group, right? Good nucleophile, bad leaving group, right? This is kind of middle of the road, right? This is more resonance stabilized. And that allows this reaction to move forward. So if we're imagining our diagram for this, right, as usual, we get to a high point in energy. That's going to be sort of intermediate A here. B is actually a little bit less stable than where we started, right? So we're going uphill there. Right? But then C, our final product, is, since it's resonance stabilized, I got messed up on my table there. It's actually a little bit better. All right, so hopefully that makes sense. You're comparing the strength of the charged molecule. In this case, hydroxide's pretty reactive, making something that's actually a little bit more reactive. But then by nature of, you know, our product being an acid, it kind of gets stuck. So if I form an acid with all this base around, it's going to deprotonate it, but then actually make something more stable and allow that reaction to happen. So a little wrinkle to the end of this mechanism, just having that extra deprotonation step there.